Welcome to the Chapter 3 podcast. I want to make sure that before we begin that you have already read a little bit of Chapter 3 and that you've taken some of your own notes. There's a lot to cover, and the purpose of this podcast is to make sure that you emphasize certain key points. So make sure you have your guided notes ready to go and a calculator available. Let's begin. Let's start with the first basic 5 types of chemical reactions. All right, we're going to learn a lot more about these in Chapter 4, but for now, it's just helpful to be able to identify the basic 5 types of chemical reactions. So first we have the synthesis reaction, where you have 2 elements that are being brought together. Typically this is like a metal and a nonmetal creating an ionic compound. But obviously this can also be 2 nonmetals coming together to share electrons and creating a covalent bond as well. The next type is decomposition, where we're going to be breaking a compound apart into 2 elements, 2 or more elements that is. The next one that we have here is a single replacement reaction. A single replacement reaction, you'll typically find a lone element sitting by itself, like this guy. And basically what he's going to do is if he is a metal, if this guy is a metal, he's going to cut in onto the metal on the other compound. But if he is a nonmetal, he is going to cut in and try to replace the other nonmetal in that compound. So depending on whether this lone guy is a metal or a nonmetal, he's the one that's going to be pushing out the other metal or the other nonmetal. Here's the key part. On single replacement reactions, you want to look at either the metal reactivity series or even the nonmetal reactivity series. The metal reactivity series is pretty complicated, and you can look up a list online. They're pretty easy to find. But a nonmetal reactivity, this actually depends upon a simple concept, which I think we've already talked about, electronegativity. If you have a high electronegativity, that means that you're capable of attracting electrons to yourself, right? So if you're able to attract electrons to yourself, that means that you're capable of bonding at a very high rate. The metal reactivity series will get into much detail in Chapter 4, but this is what makes single replacement reactions work. So if this lone element is high in reactivity, he will be able to push the other element out. The fourth type of chemical reaction that we want to look at is the double replacement reaction. This basically is when you have 2 compounds reacting with one another, and they basically switch partners, okay? The way that you know whether or not a double replacement reaction will work is you want to look for a precipitate or a solid product on this side. If one of these products is insoluble, then it will be in the state of solid. And if you have a solid product, that means that the reaction will proceed. Another thing to look for is whether or not you have produced a gas. If you have produced a gas, this also will create a situation in which the double replacement will work. And the final thing that you want to look for is a liquid, including water. If you form water or ammonia, that's typically the other liquid that we usually see, that will also make a double replacement reaction work. So you have 3 constituents that you want to look for when you're looking at whether or not a double replacement reaction will work. Was a precipitate formed? Was a gas formed? Or was a liquid, including water, formed? All right, the 5th and final type of chemical reaction that we look at are the combustion reactions. Typically what you want to see is you want to see something called a hydrocarbon. A hydrocarbon is anything that contains carbon and hydrogen. But these hydrocarbons can sometimes also include oxygen in their formula. But no matter what, on a combustion reaction, even if the hydrocarbon contains oxygen, these things need to burn in the presence of oxygen, O2. So you will have 2 reactants. You'll have some compound burning in the presence of oxygen. And the products of a combustion reaction are carbon dioxide and water. The next topic that is discussed in Chapter 3 is how to balance chemical reactions. So I want to make sure that you are aware of the law of conservation of mass, which states that whenever we have a chemical reaction, matter can neither be created nor destroyed. And typically when we draw out a chemical reaction in the form of symbols, like what you see here, the symbols of the formulas, what we'd like to do is we'd like to make it so that the number of atoms on either side of the arrow from the reactant side to the product side, that they are the same. And right now, when you look at this particular chemical reaction, you will notice that the number of carbon atoms are identical on both sides, but we have a problem. The number of hydrogen atoms and the number of oxygen atoms are not the same on both sides. So do you know how to fix this? When we balance chemical reactions, we use a number in the front called a coefficient. Coefficients will add more of the compound that you need in order to balance the overall equation or reaction. All right, so when you attack this particular equation to try to figure out how you want to balance it, we want to look at the atoms that occur the least often. Let me see if I can explain that to you. Over on the left side, I see carbon here, and then on the right side, I see carbon, right here. So in other words, I see carbon twice. Now, let's take a look at hydrogen. Hydrogen, I see here and here. So we see hydrogen a total of twice. Now let's check oxygen. Here, here, and here. Do you see how you see oxygen 3 separate times in the overall equation? That must mean that oxygen is pretty tough to balance. So we should probably balance our oxygen last. So for us, I think what we'll do, since carbon is already balanced, why don't we try to balance the hydrogen first? And the way you balance is you place large numbers called coefficients in the front of each formula in order to double up or increase the number of compounds that you've got. All right, so zero in on hydrogen. Let's see if we can balance this first. On the right side, we don't quite have enough hydrogen atoms, right? Hydrogen here is indicated by the blue. So if I need to increase the number of hydrogens, I'm going to place a coefficient in front of the water. Let's increase the hydrogen from 2 to 4. And that means I will place a 2 in the front. Basically what I'm doing is I'm increasing how many water molecules I have. So now it looks like if I put a 2 like that in the front, now it looks like I'm going to have another water molecule. Hold on, let me draw it in. Here's my extra water molecule. Cool, right? So if you see over on the right side of the arrow, make sure you're splitting your screen here. On the right side, looks like I have 4 blue hydrogen atoms. Do you see how you have 4 blue hydrogen atoms on the left? Yay! I balanced my hydrogen. So now I have 4 hydrogen atoms. Great! But when I place the 2 in front of the water, not only did I increase the number of hydrogen that I have, but I also increased the number of oxygen that I have. So I need to make sure that you keep track of all of this. Every time you add a coefficient, you're going to want to make sure that you incorporate that coefficient into all the atoms that you placed it in front of, right? Okay, well, now I've got 4 oxygen atoms total. Now, look over on the left. Here is your oxygen right here. How can we increase this so that we have a total of 4 oxygen atoms instead of just 2? I think you guys can see it, right? Place a coefficient of 2 in front of there, and I just doubled the amount of oxygen that I have, which brings me to 4 oxygen atoms. All right, so that's how you balance. You place coefficients in the front. Just make sure when you do a coefficient in the front of something that you, like I mentioned, that you need to kind of it's like foiling, like in algebra. You need to foil that coefficient in. And remember, with foiling, you multiply, right? So make sure you multiply that coefficient in properly. I hope you guys are noticing that I like to use a lot of models when I'm trying to show how to balance chemical reactions. So here's another chemical reaction where propane is being burned or combusted. Take a look at the way that we modeled the overall balanced chemical reaction. This is kind of a hot topic in AP Chemistry. In fact, many times they will ask the student to pick between several options the model or the picture that best represents a balanced chemical reaction, or maybe ions dissolving in water, and you have to be able to pick the right one. So remember, when we place those coefficients in the front in order to balance a chemical reaction, we are increasing the number of that molecule that you place the coefficient in front of. So just make sure that you're trying to visualize these things very carefully as we proceed in AP Chemistry. So here we go. We're going to start switching gears into discussing stoichiometry. Oh, don't be scared, don't be scared. It's really not that bad. So to simplify things, we're going to have a short conversation about what stoichiometry basically is. So if you just got hired to a sandwich factory and you have to keep your job, you need to make sure that you know how to make a sandwich properly, right? So you're going to probably go through some training on how to make a sandwich. So you get told that a sandwich is going to need 2 slices of bread, 4 slices of meat, 1 piece of cheese, 1 piece of lettuce, and 2 slices of tomato. And that is their way of making their perfect sandwich. So what if your boss comes to you and says, all right, I want you to make the maximum number of sandwiches, and they have to be complete, okay, because we taught you how to do this. I want you to make however many perfect sandwiches that we can with the following supplies. So the best strategy to figure out how many total sandwiches you can make is to look at each individual ingredient to figure out the maximum that that particular ingredient can make. So you were told that in order to make a good sandwich, you would need to have 2 slices of bread, correct? So if I gave you 16 slices of bread, how many sandwiches would that make? 8. If you had 5 slices of cheese, I think a perfect sandwich only needs 1 slice, right? So this could make a total of 5 perfect sandwiches. All right, do you remember how many slices of meat that a perfect sandwich needs? A perfect sandwich is supposed to have 4 slices of meat. Okay, so how many would that be? It looks like you can only make a maximum of 4 perfect sandwiches, and you'll have a little left over, but remember, your sandwich has to be perfect. Sometimes we have leftover ingredients that are going to be left over. And this is true in chemical reactions too. Sometimes we don't use all of the reactant, and so there's going to be some left over. All right, how many pieces of lettuce does a perfect sandwich need? A perfect sandwich only needs 1 piece of lettuce, so technically this guy could possibly make 10 perfect sandwiches. And then I think I said that a perfect sandwich has to have 2 slices of tomato. So you see how we might have a little bit extra here? We can make a total of 7 perfect sandwiches, but we're going to have an extra slice of tomato left over. So looking at all these values, if this was what you saw in your supply cabinet, what would be the maximum number of perfect sandwiches that we could possibly make? You're right. We can only make this number right here. Because at that point, after we make 4 sandwiches, you will no longer have any meat left over. And so this is the same concept that we use to describe stoichiometry. So in chemistry, what we like to call a limiting reagent or a limiting reactant, that's basically the substance that's going to run out first and will basically stop the production of your product. So let's take the example of the decomposition of water. One of the most important things that you're going to have to remember is that before you do any math in stoichiometry, you've got to balance the chemical reaction. So you'll notice that I've got some coefficients sitting in the front, okay? All right, so in the above balanced reaction, if I gave you 2 moles of water, how many moles of hydrogen gas would you make, and how many moles of oxygen gas would you make? Okay, in order to answer that question, you always want to look at those coefficients. So remember, try to visualize these things. Even though we're sitting here looking at symbols and everything, try to picture in your head what this would look like. If I handed you 2 water molecules, you would be able to make 2 hydrogen molecules and 1, because there's no coefficient, 1 oxygen molecule. Remember, coefficients are just like moles. So if I give you 2 moles of water, you will make 2 moles of hydrogen gas and 1 mole of oxygen gas. So that's an important concept. Coefficients are moles and moles are coefficients. Now let's switch gears. What if I only gave you 1 mole of water? If I only gave you 1 mole of water, that is kind of like half of what you initially had, correct? So if I half this, that means I'm going to half that, and I will also need to half this. That means 1 mole of water would produce 1 mole of hydrogen gas and half a mole of oxygen gas. Now, if we want to talk stoichiometry, let's change the question just a little bit. I'm still going to give you 2 moles of water, but now I want to know how many grams of hydrogen gas I will produce. So, if I give you 2 moles of water, you will make 2 moles of hydrogen gas. Now I want to know how many grams is that. So if I give you 2 moles, this is what I'm starting with. Always start the problem with what they give you. If I give you 2 moles of water, the question is asking you to give me how many grams of hydrogen gas at STP. So I'm starting the problem with what they gave me, 2 moles of water. There is a ratio going on here. For every 2 moles of water, I will make 2 moles of hydrogen gas. So watch how I use my stoichiometry. I am going to do a mole ratio right here. For every 2 moles of water, you see I'm cross-canceling my water with moles of water, I will be making 2 moles of hydrogen gas. So what this is right here, this is a very important concept in stoichiometry. This is your mole-to-mole ratio. Mole-mole ratio. You always have to have some kind of mole ratio in stoichiometry in order to do your calculations. And notice I'm cross-canceling the moles of water. I now know, you can kind of tell, you can do this math in your head. I'm just showing you how to do the stoichiometry. We know that we will definitely be making 2 moles of hydrogen gas, but we could have done that in our head. Let's get to the mass. So I'm going to change my moles into mass. And the way you do that is you have to use molar mass. Watch me cross-cancel. The molar mass is the mass of 1 mole, right? So you see how I'm putting 1 mole of hydrogen gas down on the bottom. Now on the top, I'm going to put the molar mass of, be careful, H2. This is the formula. You see the formula? Make sure that if you see little subscripts go into your molar mass. So don't just do the mass of just 1 hydrogen. Let's do the mass of 2 hydrogen atoms bonded together because it's a molecule. Remember, try to visualize what you're doing here. And the molar mass of hydrogen gas would be 2.02 grams if you're doing the molar mass to 2 decimals. All right, you can pretty much do this in your head, right? 2 times 2.02 is going to give you 4.04 grams of hydrogen gas at STP. So we're going to use the same strategy I just showed you on this next problem. How many liters of O2 gas at STP can you make? So same strategy, start with the 2 moles of water. And the heart and soul of stoichiometry is the mole-mole ratio, which comes from the balanced chemical reaction. So I'm starting with 2 moles of water, and I'm trying to figure out how many liters of the O2 gas, which is over here. This is actually a 2-to-1 mole ratio. So I like to kind of keep track of what the substance is when I'm doing my work so that I make sure that I cross-cancel with the right stuff. All right, so I'm starting the problem with 2 moles of water. I'm going to cross-cancel with moles of water. From the balanced reaction, the coefficient here is a 2, so I'm going to put 2 moles of water on the bottom. And I'm going to put 1 mole of oxygen on the top. Okay, now they're asking you to get to liters of oxygen gas at STP. So you need to remember that one conversion about how 1 mole of gas at STP is equivalent to 22.4 liters. So just make sure you're cross-canceling. So we're going to go now and convert the moles to volume. For every 1 mole of oxygen gas at STP, you're going to have 22.4 liters. And the best part about this particular problem is you don't really necessarily need a calculator here. All right, you've got the 2 up here on the top, you've got the 2 down there on the bottom, and those are going to cancel, right? So the answer here is actually 22.4 liters, and you may have been able to do that in your head, but I'm still showing you how to do the stoichiometry work. It's just good practice for you. Let's do this last one. How many molecules of oxygen gas at STP can you make? Okay, so starting with the 2 moles of water, 2 moles H2O, from the balanced reaction, this one they want you to go from the water to the oxygen. So we're going to cross cancel here with the balanced equation. For every 2 moles of water, you will make 1 mole of the oxygen gas. All right, everything's cool. But now they want you to get to molecules. So at this very last spot right here, for every 1 mole of oxygen gas, you will have 6.02 times 10 to the 23rd molecules. All right, so you don't necessarily need a calculator again, do you? Because as you can see, the 2 here and the 2 here, they cross cancel. So the correct answer is actually 6.02 times 10 to the 23rd molecules. Pretty easy, huh? So let's apply what we just learned to a brand new problem. And remember, in stoichiometry, typically it's just like looking at your storage closet and seeing what you have and figuring out the maximum you can make. So in this example, they are providing you with 6.7 moles of sodium and 3.20 moles of chlorine. And what I like to do is always start with a balanced reaction. Like I said, you can't do stoichiometry without a balanced reaction. And they're providing you with 6.70 moles of this, and they are providing you with 3.20 moles of that. And obviously they want to figure out what is the maximum amount of the sodium chloride you can make. So the best plan of attack is very similar to where you got a job as a sandwich maker. What you're going to do is you're going to figure out how much this amount could potentially make of sodium chloride first, and then you're going to figure out how much of sodium chloride that will also make. So however many ingredients they give you, you're going to figure out the maximum each one of those could potentially make. So always keep that balanced chemical reaction in your mind. So in this particular example, you're starting with the chlorine, and let's figure out the maximum amount of sodium chloride you can make. So if you look down here, for every 1 chlorine, you will be making 2 sodium chlorides, right? That's the ratio, 1 to 2. So you'll notice here that I am cross-canceling with chlorine and chlorine, all right, so that I can get to the NaCl. And you can kind of do this in your head. You don't really need a calculator here. This would be 6.40 moles of NaCl. All right, so what this means is that the maximum amount of sodium chloride that the 3.20 moles of chlorine can make would be 6.40 moles. Now let's do the same thing to the sodium. But before we answer that question, hey, this is my daughter. Her name is Caitlin. That's totally an extra credit opportunity, okay? Right there. So this time we're going to check to see, we're going to go from the sodium now to the NaCl. So you see how the ratio in the front is a little bit different now? All right, so same method, cross-canceling. This time you're cross-canceling the moles of sodium. And again, you can kind of do this in your head. The 2 and the 2 here, right here, they cancel. So the maximum amount that the sodium can make would be 6.70 moles. So now we just need to compare what we got. All right, so time to compare. With the chlorine, you can make 6.4 moles. And with the sodium, you can make 6.7 moles. So what is the maximum amount that you can make? Let's see. So there is a reactant that is going to run out first. And I think you guys can tell that the reactant that produces the lesser amount is going to be called the limiting reagent, the reactant that runs out. So this is your lesser amount right here. That means chlorine technically is going to be completely gone, and we would call chlorine your limiting reagent. Sodium, yeah, we used most of the sodium, but it doesn't look like we used all of it. So your sodium was technically in excess. And the maximum amount that you can make, sometimes called your theoretical yield, is 6.4 moles. So the lesser amount is your theoretical yield, the maximum you can make. All right, so let's take a look at a fresh example. First of all, I want you to notice, yes, the reaction is balanced. Now, instead of starting you off with moles, I'm going to be starting you off with 2 different masses. So the strategy here is that you have to get to a mole ratio because that's what coefficients use, right? Coefficients are like moles. So the fact that you were given these masses to start with, the very first step that you need to think about is converting these masses into moles, right? Using the balanced reaction. That's where your mole ratios come from. And then you'll want to notice that they want to know what the maximum amount of sodium sulfide you can make, and they want that to be ended in grams. So after you do a mole-mole ratio, you need to convert that final moles into mass. All right, so that's the strategy. So pause the video right here, take your time. You will be starting 2 problems, one for the 14.2 grams of sodium and one for the 12.9 grams of sulfur. Take your time, pause the video. Don't move on until you tried to do this by yourself. All right, so this is the solution here, all written out for you. So let's take a look at this. Let's see what the strategy was here. So you'll notice that there's 2 different problems, one for the sodium and one for the sulfur. And the fact that we started with mass, we're going to convert that mass to moles. This right here is molar mass. Then what we did is we cross-canceled, we're always cross-canceling here, we cross-canceled here with the coefficients from the balanced reaction. So first you did molar mass, then you did the coefficients from the balanced reaction. Now if we stopped here and we cross-canceled everything, you would actually be at moles of Na2S. The last step, you have the molar mass because you converted your moles to mass. Now look at the second example here with sulfur. This is the molar mass of sulfur, this is the coefficients from the balanced reaction, and this right here is the molar mass of the Na2S. And yes, you have 2 answers, right? But which one is the maximum that you can make? The maximum that you can make is the lesser amount, this one right here, 24.1. And so we call this, if this is the maximum we can make, it is called the theoretical yield. Now remember, the reactant that made the theoretical yield, okay, must have run out. All right, so that means that sodium is technically the reactant that ran out. It's called the limiting reagent. So even though we know how much we were supposed to make, in the lab you're not always going to get that theoretical yield. All right, sometimes we call the theoretical yield the accepted value, the value that we were supposed to get. So let's pretend that you actually do this lab in a real lab setting. And basically, we want to figure out how well we performed in the lab. So all you have to do is do a calculation called percent yield, which is what you got divided by what you should have got, times 100. And then to figure out how far away you were from the accepted value, you're going to do another calculation called percent error. Percent error just basically tells you how far away you were from getting 100%. So here's one last question we're going to look at from the same example. So you used up all of the sulfur or some of it. Let's take a look back over here. So looking back at our example, it looks like the sodium is completely gone. It is finito, nada más. So sodium is completely wiped out. But you started with 12.9 grams of sulfur. Obviously, this was not your limiting reagent. That means that we actually do have some of this left. So then, what is a strategy to figure out how much of the sulfur we really used and how much is actually just kind of left over? That's the real question, and I've got a great strategy for that. Here's the idea. Start with the amount of sodium sulfide that you know you made, and based off of that quantity, let's just figure out exactly how much sulfur we used, because we know we didn't use all of it, but we know we used some of it, right? So start with what we call your theoretical yield, the maximum amount of the product that you can make, okay? Then what we're going to do is we're going to cross-cancel and get that mass to change into moles. You see how I cross-canceled grams here to get to moles. Look back at the balanced reaction. Let's go from the product to the sulfur. Sulfur, we know we use some of it, but not all of it. So you see how this is a mole ratio from the balanced reaction. All right, and if you cross-cancel here, you'll notice that you still have moles sitting on the top. So do one last step and just convert the moles into mass. Yeah, you see the molar mass being used there. Okay, so this answer right here represents the amount of sulfur that it took to make that amount of your product. You'll notice that we had way more sulfur available to us. We didn't use all that was available. We had 24.1 grams available. It looks like we only used about 9.91 grams of it. So, guys, how do you figure out how much is left over after the reaction stops? Oh, that's pretty easy, right? Don't you just subtract? So what is 24.1 minus 9.91? And that will give you the exact amount of sulfur that is left over when the reaction stops. That's the excess. All right, everyone, now we're going to switch gears into another topic. We're going to start talking about chemical formulas, and specifically empirical formulas and percents. All right, so when we talk about chemical formulas like, for example, water, H2O, carbon dioxide is CO2, when we look at those formulas, I want you to realize that those formulas technically are mole to mole ratios. So for example, sodium chloride, there is 1 sodium chloride for every chlorine atom. There is in water 2 hydrogen atoms per 1 oxygen. But you see, these formulas, they're not based off of mass ratios, but off of mole ratios. So, if I give you the percent composition of each of the elements inside of a compound, you should be able to determine the formula of the compound. Sounds tricky, huh? Here's how you do it. So what we're going to do is we're going to look at an example here. It says, determine the percent composition of sodium and chlorine in sodium chloride. All right, so you guys already know the formula for sodium chloride, so you just look up their masses, and this is what I showed you already in a previous video. To do percent composition, what you do is you do the mass of the element over the mass of the compound. That's sometimes called mole over Mach, right? All right, so you see the math set up here. What you have on the numerator is the mass of the element, and on the denominator you have the mass of the compound, and then you simply need to multiply by 100 to change that into a percent. All right, ladies and gentlemen, get those percents right now. Pause the video. All right, you should get these percents. Okay, so let's see if we can get the formula of sodium chloride based off of those percents. All right, let's give it a go. There's definitely a strategy here. So step number 1, you want to assume that you have 100 grams of this mysterious compound. And you know that in that 100 grams, 60.66% of it is chlorine, right? Wouldn't that mean that you have 60.66 grams of chlorine in there? So basically, step 1, assume you have 100 grams. That way we can change the percents straight over to grams. In other words, just literally erase the percentage and place grams instead. Now, you know that formulas are not based on mass ratios. They're actually based off of mole ratios. So step number 2, you got to change those masses into moles. All right, so use your periodic table, whip it out. Let's change those masses that we just got into moles. All right, so as you can see, when you convert both of these percents that we changed to mass, that we changed to moles, look at those answers. You can tell this is actually a 1-to-1 ratio. If you just kind of simplify, 1.7 to 1.7 is 1-to-1. Pretty cool, right? So let's see if you really have the hang of it, and let's look at a more complicated question here. So let's pretend that when you do an analysis, you actually find that this compound technically will show you like 104.9 grams of iron and 45.15 grams of oxygen. What you have here is technically a mass ratio. Remember, formulas don't come from mass ratios, they come from mole ratios. So right off the bat, we're going to change those masses into moles. There you go. So this one's a little bit more complicated. When you do the conversion into moles, you see that ratio? That's not a very pretty ratio. So we didn't have to, by the way, do anything on step number 1. We didn't have to go from percents to mass because they gave you mass. So we just jumped right into a mole conversion. All right, but I'm looking at these and I'm not really sure what I need to do now. All right, so here comes step 3. So in step 3, what you're going to have to do is reduce those ratios. And the way you do that is you just divide by the lowest value that you have. The lowest value we have is 1.878. So take both of those moles and divide by that value. Okay. Even when we do that, we still have this ratio that is not very pretty looking. It's basically a 1 to about a 1.5 ratio. All right, well, what do we do now? Every once in a while, you're going to have to create a step 4. And this is a good example. We have a ratio where you see a 1 to a 1.5. You would never see me write a formula like this, you know. I've got iron, 1.5, oxygen, you know, or I'm sorry, what is this? 1, sorry, this is the 1, and oxygen 1.5. You would never see subscripts like that. That's silly. Subscripts have to be in whole number ratios. So, every once in a while, you get to use a step 4. What you can do is you can multiply both of these ratios so that you get the least whole number ratio between the two. As you can see, if I multiply both of these ratios by 2, you'll get 2 iron, and 1.5 times 2 is actually 3. Oh, you see how that worked? All right, so that is, in a nutshell, the strategies that you need to do when you are looking at going from percent composition to an empirical formula. At the end of chapter 3, they mentioned something called combustion analysis. This is a really helpful technique for figuring out the formula of most organic compounds, which is a pretty common analysis that, you know, we have to do when we have an unknown sample. From this information alone, we can determine the empirical formula of an unknown compound. Pretty cool, right? So you may or may not have your textbook with you, but I'm going to use example 3.15, which is found on page 97 of your text. Isopropyl alcohol, a substance sold as subbing alcohol. I'm sorry, that should be rubbing. That's an awesome typo. All right. Is composed of carbon, hydrogen, and oxygen. In other words, it's a hydrocarbon. Combustion of 0.222 grams of isopropyl alcohol produces 0.561 grams of carbon dioxide, 0.306 grams of H2O, and they want you to determine the empirical formula of this guy. All right, here's the strategy. You need to remember that you're dealing with a traditional combustion reaction here, and that the only two products of a combustion reaction are carbon dioxide and water in a true combustion reaction. So, if you look at these formulas, you've got your carbon sitting right here. If you know how much CO2 was produced, and look over here, you see the hydrogen? You got your hydrogen. All right, so if we know the mass of CO2 and H2O that was produced in the combustion reaction, we will be able to have the mass of carbon, the mass of hydrogen, and then the mass of oxygen is kind of tricky because you've got two sources of that, okay? But if you have the carbon and the hydrogen, the law of conservation of mass basically says that the rest of the mass has to be oxygen. So let's start off by taking the mass of the carbon dioxide they gave us. And let's try to figure out how much carbon is actually in there. Okay, so the strategy here is pretty simple. Just take the mass that you have, change that mass into moles, all right? And then over here, what you see me doing is, in the formula of carbon dioxide, you know that formulas are mole-mole ratios, right? So for every 1 carbon, there should be 2 oxygens. But another way to look at it is this way. For every 1 carbon dioxide, there's 1 carbon. All right, so you see how that is a mole ratio between the compound and the carbon in there. And then at the very end, just change that carbon from moles to mass at the very end. So, in this amount of carbon dioxide, there is this much carbon in there. And if you think back, the original sample that we tested, this is how much carbon was in that original sample of isopropyl alcohol, or rubbing alcohol. Next up, let's look at that water. Same idea, okay, we're going to get the amount of hydrogen in that sample. So start with the mass of water that they gave you. All right, change that to moles of water. Just remember that in 1 water molecule, there are 2 hydrogens. So this is the mole ratio. For every 1 water, there's 2 hydrogens. And then just change that moles into mass again. So you see how this quantity right here is part of this. All right, so In the original isopropyl alcohol, that's how much hydrogen he had. All right, but there's one piece missing, the darn oxygen. This is where the law of conservation of mass is pretty darn helpful. This was the mass of the original sample. We figured out that in that sample, there was this much carbon from the carbon dioxide, and there was this much hydrogen from the water. So all you have to do is just subtract, and whatever's left is the mass of the oxygen. So there's really only one thing left to do. Take all of those masses that we just got and convert them to moles, because we're looking for the formula. All right, so I'm taking the mass of the carbon that I had, I'm taking the mass of the hydrogen, the mass of the oxygen, converting them to moles, and so you get these really nasty looking mole ratios. You see these right here? All right, so do you remember back to the strategy for figuring out empirical formulas? We are going to take all three of those values and divide by the smallest one there, which would be this guy. All right, let's see if we can simplify that out. All right, when we simplify, it looks like we have a nice, clean ratio. We have 3, 8, and 1. This little rule that's sitting over here is a really nice rule to just try to remember. So I feel comfortable rounding this value to 8. And here's the basic idea. The number right here in the 10th place will determine whether or not you can round. So as long as that value is not a 0.3 or higher, you are allowed to round. If it was a 0.3, you're going to need to multiply by 3 to make it 0.9, which will round the value up. All right, so that's just kind of a general rule of thumb, and I think we've seen a previous example where it was 0.5. And if it's 0.5, obviously you're going to have to multiply by 2. Well, ladies and gentlemen, that concludes the entire vodcast. And there was a lot that we had to cover, so I know it's a little bit longer. This is kind of not the norm, okay? I just want to make sure you understand that. All right, everyone, peace out, and I'll catch you next time. Bye-bye.